If you're interested in developing your own custom web search agent with the best and largest open source large language models, then stay tuned for this video. By now, we're all aware of the benefits of developing with open source large language models. Tools like Llama have been instrumental in helping us get access to open source large language models. However, many of us are still constrained by the hardware that we have. Therefore, that leaves one alternative, and that is to actually rent your own hardware, rent your own GPUs. Now, renting your own GPUs and building your own large language model server can be expensive and also difficult if you don't know what you're doing. So in this video, I'm going to show you how to build your own large language model server on a rented GPU in an efficient and relatively cheap way. You'll be able to use this server in your custom web search agent. So you'll have a completely open source web search agent built on open source large language models by the end of this video. So to follow along with this, you'll need $10 US of credit on Runpod and the GitHub repo containing the code for the web search agent, which will be linked in the description to this video. If you stay tuned to the end of this video, I will be demoing how this custom web search agent works with the Llama3 70 billion model. So if you like this content, remember to give us a thumbs up, subscribe to the channel for more large language model and AI-based content, and in the comment section, give us your opinion on the pattern and any other patterns you've used to build your own large language model inference server. Okay, let's get into the technical details. Before we dive into the setup of our inference server, I want to show you the high-level design pattern that I've used to build out this inference server. So pay attention to the schematic diagram on screen. So on the left-hand side, we have our server setup, and it's pretty simple. What we're doing is we're renting the GPU, we're renting the hardware from the GPU service, which is Runpod. And then within that hardware, we're actually going to deploy an inference server using an open source project called vLLM. And I'll talk about the advantages of using vLLM shortly. So once we have that deployed, we can access this via an endpoint. And by sending a post request from our agent.py script, which contains the custom web search agent, we can actually utilize any large language model that we deploy within this inference server. Now, let's talk a little bit about why I'm using vLLM specifically. So vLLM, from a cost and throughput perspective, is much more efficient than a lot of the other inference strategies that you might have come across. So the most popular one I wouldn't say the most popular one, but one of the more well-known ones for open source large language models is to use the Hugging Face API directly. But you can see the throughput for the different types of Llama model here. vLLM is actually higher by a significant amount. So it actually quotes it's 8.5 to 15 times higher in terms of throughput than Hugging Face, and also 3.3 to 3.5 times higher in terms of throughput than the text generation inference server, which is another popular project. So obviously having a higher throughput means more efficiency, but it also means reduced costs too. So that's why I'm choosing to use vLLM as the inference server. There are other advantages to vLLM too. It supports a wide array of open source models. So pretty much most of the models you see covered on Hugging Face and their variations, their fine-tuned variations, can be deployed in the vLLM inference server. It supports quantization. So for those of you that don't know, quantization is a method that allows you to use large language models at lower precision, which means reduced hardware costs because of the reduced memory requirements. So vLLM supports various methods of quantization. It also supports multi-GPU inference. So for some of the largest large language models, you need access to GPUs with a lot of VRAM. And sometimes getting access to the A100s or H100s can be difficult. They're in such high demand. But what you can do with vLLM is actually string multiple lower VRAM GPUs together and have your large language model operate across those. So vLLM is useful because it supports multi-GPU inference. And the last thing here is it's easy to get started. So I've created templates on Runpod to help you get started, and we'll be going through those in this video. So by the end of this, you should be able to get started with vLLM and build your own inference server. Okay, let's explore the setup next. To set up your inference server, you'll need to know the memory requirements of that server. So the best way to do that, or the best approach I've found to do that, is to navigate to this application on Hugging Face, which is called Can You Run It? So what you can do on Can You Run It is you can take the model that you want to deploy. In our case, we're going to be deploying Llama3 70 billion instruct. And there is a menu here. I won't open it because it reveals my Hugging Face API key, which I don't want to expose. But there's a menu here where you can actually select the model you want to work with. So it can be any Hugging Face model. And some of the models, because they're gated, you'll need to provide your API key. So just bear that in mind. There is also the ability to select the hardware. So if you are working on fixed hardware, you can actually see if a model is suitable to run on that hardware directly. In our case, all we want to do is understand the memory requirements for inference. So if we scroll down for Llama3 70 billion, we can see that the memory requirements here are stated for holding the model. So this is the total size of the model. So if we did it at full precision, we've got 259 gigabytes. At float 16 or half precision, we have 129 gigabytes or 130 gigabytes. And then at various levels of quantization, so int 8 and int 4, we can see the memory requirements. So we are going to hold this at half precision. So we're going to hold it at float 16. And we need to understand the memory requirements for storage, which is this up here. So we need at least 130 gigabytes for storing this model. And then we also need the memory requirements for inference, which is around 155 or 156 gigabytes. So we know that when we're setting up our inference container, it needs to have met these memory requirements. We're not doing any fine tuning here, so we don't need to worry about training or LoRa fine tuning, just the top two. Once you have your memory requirements, you can navigate to Runpod and we can get started with setting up the inference server on Runpod. As a quick note, as the time of recording this video, the Meta Llama version of Meta Llama3 70B instruct wasn't available to me on Can You Run It? So I've used the news research version, which is, I believe, a clone of the same model. So in terms of the memory requirements, it's going to be roughly about the same. On Runpod itself, I will be deploying Meta's version of the model. Right, now that we know our memory requirements for the inference server, we should navigate to Runpod. And once you're on the Runpod site, you want to navigate down to templates. And of course, if you're new to Runpod, you'll want to make sure that you have at least $10 US of credit stored on your account so that you can follow this tutorial. So just make sure you have that $10 US of credit to work with. So you'll navigate to templates, and I have already set up a Llama3 instruct 70 billion template. I'll provide a tutorial version to go alongside this video, so you'll be able to use that. But let's go into the template to see how it works under the hood. So templates on Runpod are essentially just Docker images that you can set up. So you want to give your template a name, and I've given the name vLLM Llama3 instruct 70 billion so that I can refer back to it. The template uses the vLLM Docker image, the official one, as a base. So that's what we've set here as the container image. Then we set some arguments. So these arguments are really important if you're working to build your inference server with vLLM. So these are vLLM specific arguments. So we have the model, and we set this to the model we would like to use, and you should provide the full Hugging Face path for that model. So we're using the Meta Llama 3 70 billion instruct model. The data type here, we're loading the model in float 16, so that's half precision. Enforcing eager gives us the ability to benefit from some efficiency in terms of GPU memory utilization. I think it's also at the cost of latency, but for this tutorial, that is fine. And then finally, tensor parallel size. So I did mention at the beginning of this video that we could have a model using multiple GPUs with vLLM. To understand tensor parallelization or model parallelization, you've got to understand how attention mechanisms work for large language models. So in short, attention mechanisms can be calculated in parallel. So for any large language model you're working with, whether that's Llama3 or anything else, you'll have a number of attention heads. Usually it's an even number of attention heads, and you can get the model to operate over multiple GPUs by splitting those attention heads across multiple GPUs. So in this case, where we've set tensor parallel sizes 4, we will be splitting our attention heads across 4 GPUs. It is really important that the number of GPUs that you choose to split over divides into the number of attention heads of the model that you're working with. So that is a really important consideration. The number of attention heads of the model you're working with must be divisible by the number of GPUs you select. It's not always clear how many attention heads the model has. Sometimes it's published, other times it's not. You can figure it out through trial and error. So I would usually start with 2 and then work my way up. An even number of attention heads usually works, but if it does fail, you will see it in the logs when you do try to deploy this container. And usually in the logs, it will tell you how many attention heads the model has. Sometimes attention heads, the number of attention heads the model has is published on the model card on Hugging Face. Other times you might be able to find it if there's a research paper that accompanies the model, you might be able to find it in there. Sometimes it's more difficult to find. So if you can't find it, you can start with trial and error and figure it out from the logs. That usually does the trick. Then we're setting the container disk and volume size, and this obviously just needs to be enough to hold the model. Container volume is important here because when we stop this container, if we want to restart it, all of the model weights will be in that container volume, and we just simply have to pull the model weights from that volume instead of re-downloading the model from Hugging Face. So that's why we set a volume disk. Don't change the volume mount path. That's the default path written by Hugging Face, so I wouldn't change that. The other important thing to bear in mind here is if you are using gated models, you must set an API key for Hugging Face in the environment variables. And that's how Hugging Face can detect whether you have access to that gated model or not. So if you're using Llama3 or you intend to use Llama3, I think you still have to request permission to use it. So you have to have a Hugging Face account and sign up and request permission to use Llama3 via Hugging Face. Then you should navigate down to the environment variables and put your API key from Hugging Face into the environment variables. I'll have that outlined for you in the template. So when you're doing this yourself, all you have to do is go into the template itself and set your Hugging Face environment, your Hugging Face API key. I'm not going to show you this because I don't want to expose my Hugging Face API key in this video. That's it for getting set up on the template itself. When you're ready to deploy this template, what you'll do is navigate to pods. So I have one deployed earlier, but I'll show you how this works if you want to deploy it yourself from scratch. You hit deploy, and then you'll be presented with a number of GPUs that you can rent by the hour, and the price and availability is outlined here. I would always select high availability GPUs. So the trick I use is if I'm just doing something for experimentation, I'll navigate down to the previous generation. And we are going to use the high availability A40s here. So you can select the A40 GPU. You can also select the RTX A6000 as well. I mean, these have 48 gigs of VRAM. So let's select the A40 because it is cheaper. And then remember, we set our tensor parallel size to 4, so we'll need 4 GPUs. We'll hit the on-demand pricing. You can get it cheaper if you hit spot, but that's much less available. So let's hit on-demand. If you want to make edits to the template before you deploy it, obviously mine is already set because I'm already setting this as a default template, but you will choose your template here. If you want to make edits to your template before you deploy it, you go to edit template, and then you can change anything about the arguments for the vLLM server within the template. So if you want to use a different model or you want to use a different number of GPUs, you can change that all here. Or if you want to add additional arguments from the vLLM engine. So if you want to do things like quantization, for example, you can change that here. And you just set the overrides and you're ready to go. And then when you're ready, you can deploy on demand. Once you're ready, you hit deploy, and that will build your container in the background, and there'll be logs available for you to explore how that is working. So it does take some time to build. You can see we're building everything out here. Once that's built, I will show you the logs and show you how to troubleshoot that. So our container is now built, and this is the dashboard you'll see once the container is built. So there's a few things to notice here. Notice the volume usage. So we're storing the entire volume of the model here. So all the layers of the model is stored in the volume. Notice also the GPU memory used, right? So we have that GPU memory distributed across 4 GPUs, and that matches the tensor parallel size that we set earlier in the image. And then we have our running costs down here of $2.76 per hour. If you want to monitor if this has successfully deployed or not, you can navigate to the logs. Within the logs, you have container logs. So if I scroll up, you can see those container logs, and that also the container logs obviously monitor the actual model itself. So if you're making queries to the model, it will come through these container logs. And then there's system logs. The system logs will tell you whether the container started successfully or not. So usually any errors will come through the system logs or the container logs, and you can debug from there. Okay, so we have our vLLM server up and running. The next part is how do we actually connect to this server? So it's really simple. If you hit connect, there is an HTTP endpoint here, and we can connect to that by simply grabbing the URL here. So if you do see this black screen, detail not found, that is what you want to see. That means everything has set up correctly. So as I said, you want to copy this URL out, and that's the URL you use to connect in your agent script to your model that is deployed on Runpod using the vLLM Inference server. So in the next part of the video, I'm going to take you through how to use that within the agent script. I'm not going to go into detail about the agent script itself because I have another video doing that. So I'll link that in the description to this video. So if you do want to have a deep dive on the Python script for the agent itself, you should watch that video, and that will give you everything you need to know. Okay. We have our server deployed on Runpod. So now we are navigating to the agent.py script within the custom agent project. And what you want to do is you want to navigate to the bottom of the agent.py script and paste the endpoint for your Runpod vLLM inference server where it says Runpod endpoint. So there's a few things to be aware here. First, the model must match the model that you have deployed within the container. So this should be the full Hugging Face path, and set all of these to the same model. The other thing to be aware of is with Runpod, if you're using the vLLM inference server, you want to set a stop token. So what that essentially means is it tells the large language model when to stop generating text. So when you're using open source models, especially the instruct variety of open source models, they all come with their own prompt formats. So the Llama3 series of models has a certain prompt format. The Mistral set of models has a certain prompt formats, and these prompt formats will also provide a stop token. So you want to make sure that whatever model you're using, the stop token aligns with the stop token for the model. So you just set that here if you decide to change from Llama3. So this will be set in the script to this. That's for Llama3, but if you're going to use Mistral or something different, you want to change that stop token. As I said, I'm not going to go through the agent.py code in detail because I've already done that in a previous video. So if you want to understand how the agents work together, please watch that previous video, and I'll link that in the description to this video. But what I will do is I'm going to demo how this large language model powered agent works with a simple question. So you get to see how it works with the Llama 3 7B instruct model. So I'll hit save on that, and I'm going to pull up my PowerShell. So within PowerShell, I can write Python. Apologies, there's some weird formatting here. Python agent.py run. And what that's going to do is going to set up the agent script. It's going to get us up and running. So then it asks for the query, and we'll do something really simple, like what is the current weather in NYC? Let's try that. So this is connecting to the Runpod server that we set up. So we have our Inference server connected to, and you can see the planning agent has come up with a list of search queries, and it's also identified the most important one. So it says current weather in NYC is the most important one, which makes logical sense. Now we're searching current weather in New York City. And this should return a search engine results page from which we'll pick the best page to actually go and visit to get that data. So that's all running in the background. Aha, so we've done that. It was relatively quick. So we pulled out the search engine results page, and then it's identified the best pages, weather.com/weather today, and it's Manhattan, NY. So let's just make sure that it is actually pulling from there. So yeah, that's the source here, I believe. Yep, that's the source we've picked up. Actually, no, hold on. That says Harbor Hour. We actually want weather today, L. Yep, so it's the top source that we picked up. And then we've scraped the data from that page. And the integration agent has then returned a response. So it says, based on the research provided, the current weather in Manhattan, NYC is, and then we've provided some weather, and there's a source there. So there's a citation. And then we've checked it to see if it meets the criteria. There's a criteria dictionary here. If you want to know more detail about this, look at the previous video. The response is true, so it meets the criteria, and we deliver the final response. So it says, as of 9:23 a.m. EDT, the temperature is 74 degrees Fahrenheit with rain showers. So and it provides a source. So let's just check the source to make sure that we have actually done that correctly. So that should be opening in another window. Just pull it up. There we go. Okay, so we have the source. Just accept the cookies. So let's pull that up. And it says, what does it say? So it says 75 degrees Fahrenheit, which is what we've identified. It says rain and showers, 93% occasional thunderstorms. So let's just see where that's all coming from. Okay, yep. So that looks largely correct. Let's see the wind. Wind is 1 mile an hour. So that looks largely correct. So it looks like the Llama3 70 billion model has correctly found out that information, which is great. So I will be producing some videos to really test these models against the OpenAI models and testing a wide variety of the models. So I'll do the Llama3 70 billion models. I might do the mixtural models as well. I might do some coding models to see how well they work as agents. And I'll be comparing them with the models from OpenAI. So I'll be comparing them with GPT 3.5 Turbo and the state-of-the-art model that's just recently been released, GPT 4.0. So stay on the lookout for those videos. Okay, so I know it's not ideal to have to rent GPUs, but ultimately it does give us access to a wider array of large language models, and we can test more of the really large and high capability large language models by renting GPUs. What I've showed you today is a quick and easy way of building your own inference server that anybody can do. If you like this content, give us a thumbs up. Remember to subscribe to the channel and give us your opinions about the vLLM inference framework that I showed you. And if you use any alternative ways to create your own inference framework for running those really large language models. Thank you, and I'll see you on the next video.